Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide, and this is Semester 2 2025, and this is a revision seminar for Statistical Modelling and Inference. The last revision seminar for Statistical Modelling and Inference, because even if this course exists at the university, it'll have a new name. So, yay, and hopefully they've rewritten it so it's better. But that is true for all courses, but in case you're watching this, anyone who wrote the original version. So I've been given one request, which is whatever the question version of, we're a bit confused about how everything in this course fits together. And then I went and looked at everything in the course, and these are the titles of the modules, of which there are 12. Which seems not unreasonable considering there's 12 weeks, but when you look at the stuff that's in each of those modules, I really do, my professional opinion is there's too much stuff in this course. So your feelings are valid, whatever they are, about this course. So I'm just going to talk for a bit, and then maybe we'll dip into some things that are specific, that people have come up with specific questions as we go. I will say that this is your seminar. Interrupt me. It's totally fine. Maybe not more than once a sentence. And correct me. Like if there's something doesn't sound right from based on your experience of being in the course, let me know because I wasn't there. So, yeah. Okay. So I always like to say that SMI is to first year statistics as real analysis is to first year calculus. Like SMI is the real analysis of statistics. That's exactly what it's supposed to sound like. If you're studying real analysis, it will feel similar in vibe in terms of what you're doing. And so it strongly assumes that you've done a statistics course before that mentions various statistical things that this course contains the proofs of. Does that sound right? Yeah. And so there's a reason why this list contains the similar things that are in a first year statistics course. It has p-values and inference for samples and regression, and all of those things are in a first year statistics course. And there's a couple of extra spicy things that make it possible to prove some of those things. Pivotal quantity you've never heard of until this year, and that's designed specially to allow us to argue proofs for confidence intervals, more or less. Okay, so that's the idea, and it seems to me that it would be useful to just have in my mind some of the things that are in first year stats courses. And so traditionally there are 4 different kinds of statistics that answer 4 different kinds of questions. One of them is what's going on, which is descriptive statistics, and this course is not about descriptive statistics. It is about inferential statistics. And so there's what's going on, which is normally graphs. So no, that's not what this is for. Technically, estimation is under this heading. And then there's yes or no, which is what hypothesis testing is for, to help answer yes or no questions. And the way you answer them is via a p-value or a critical value, whatever. Same concept. And then there's what's this number, which is what a confidence interval is for. And you say, well, I'm going to give a range of possible answers for the number because I'm a statistician. I'm never going to give you just one answer because I know that I will never know what the real answer is, so I'll give you a range. And then there's basically what's the formula? which is what regression is for. And you may note that to do regression, you end up having to do both of these things usually somewhere along the way. And so these both kind of feed into the regression the other way. And these two things are strongly related to each other because they use the same data in opposite directions. So that is the general idea. And so what this course is structured like, it goes back and forth between these things. Like the second half of the course is more or less regression. That's all regression of some type. Technically, back in first year, ANOVA was in the p-values section. But they've moved it to regression because we've learned a few things about how ANOVA works. And we do some of these things again in the regression section, but you see that more than half of the course is about regression. So it's probably worth talking about that. Okay, cool. But then the other bits has confidence intervals and hypothesis tests, like right at the start, because that's what it's about. Right, okay, cool. So for me, for all statistics, whether SMI or not, a useful organizing thing to keep in your mind is that if you're going to calculate any probabilities, you need to know the entire distribution of something. So while a p-value is a probability, officially, no probability exists without all the other probabilities. So you have to know what the distribution is, which means you need to know all of the things that could have been and how likely all of them are. That is what it's about. And we've fiddled with this idea a little at the end when you get to likelihood, but it is the same idea, that you have to know something that controls the distribution. And in this course, you learn some distributions specifically for the purposes of doing hypothesis tests. So in other courses, maybe in Prob and Stats, you learn some distributions that go with modelling certain real-world events, like the Poisson distribution and that sort of thing. But in this course, you learn some distributions that go specifically with the calculations of test statistics, more or less. And so a big part of the theory is distributions. Yeah, and everything that is a probability statement is involved with knowing a distribution. So confidence intervals are about probabilities. You have a 95% probability of creating a confidence interval that contains your parameter. With hypothesis tests, the p-value and the type 1 error and the type 2 error and the power and all of those things, they're all probabilities as well. And so there are many probabilities listed in all of these things, and they all require a distribution. So it seems to me that that's a useful way of thinking about it. And that's why we need a list of distributions. Okay. And that's why they kind of strongly assume that you've done probability and statistics too. But well, I know it's an assumption, it's not necessarily a truth. You'd think that statisticians would be better at assumptions. Anyway, so right. Right, cool. So there is just making up crap at the moment, but I think this is good crap that is helpful, and it helps me hold on to things. Okay, right. So it is useful to have as your model of thinking about even hypothesis tests that the goal you're thinking of answering is always, like from a science point of view, is always a what's the formula sort of question. You're always thinking about one thing being able to help you predict another one. even when you do a t-test. And they did a proof on that later on, but that's how I organise things. So I'm just going to do a quick scroll and see if I can find the all the hypothesis tests in this course that are mentioned. So here we go. And maybe what I'll actually do is I'll search for the word test, of which there are 322 instances of in this course. Fabulous. Maybe oh no, it's going to be too hard. I'm just going to have to scroll. There's so many of them, right? So far, we've mentioned the Z test for a single mean here. I'm just going to write them down as I go. Which goes with knowing having a set of normally distributed measurements and you know the standard deviation of them. Oh, good. It's good for me to know that they list normal distributions with the variance in this spot instead of the standard deviation. I'm just going to pop that down for myself. Different courses have different, sometimes they put sigma in that spot, sometimes they put sigma squared, so it's sigma squared in this course. Okay, cool. So far we're working entirely with test of a single mean. Power, I'm just skipping the power things, I'm just one-tailed. Just going to write that down. P-values, confidence intervals. Haven't found a new one yet. So far we've gotten quite a long time and we've only been using this one test. All the way up until this point, everything so far has been about this one test, the Z test for a mean. Okay, doing well. Now we have a list of distributions. Cool, we'll come back to that. And here we go, t-test for a mean. And the difference between this and the other one is that we have an S in the spot where there used to be a sigma. Cool. Okay. Sure. We made an F distribution. And then they're just saying it again. Oh, we've got a chi-squared test for a standard deviation. Well, variance, technically. Well, it's a confidence interval anyway. I hope you don't mind me just doing this. I don't think that it's pivotal quantities, which are a way of proving things. Now we've just here created a confidence interval for two independent samples with the same standard deviation. That's what this one is. Two independent samples, the same known sigma, and then we have two independent samples with the same but unknown sigma. And these are about means, these ones. Now we've got two independent samples with known but different sigmas. Okay. Different known sigmas. Okay. And then presumably there'll be one with different but unknown sigmas. No. Maybe that's coming later. Is that coming later? Okay, and now we're in regression. Okay. How fascinating. I'm just going to look at the example. Huh. So in this one it says what the two variances are. Oh, this is a sample variance. Oh no. Oh, we have an F test for comparing two variances. So this is our different but unknown sigmas here, this example here, because if you look at the text, they've used the S's in the sample stand deviations just here. They've used S's, whereas back here they used sigmas. But this is the S's here, so that's a T distribution. Bear with me. So we didn't have different but known. Just give me a second. Oh, so I was just looked at this and assumed that we had different but known sigmas. But in the next line we have different but unknown sigmas because they're S's instead of sigmas. Oh, okay. Mm-hmm. But the general rule is if you know what sigma is, you'll get a Z. And if you don't know what the sigmas are, then you get a T. And be careful, you've got to see whether, when I say don't know sigma, that means you don't know the population stand deviation. If they tell you the sample stand deviation, then you're living in the land of T. Okay. But then we actually have here a test for two variances. Because look at this. The question says, do these represent sufficient evidence to suggest a difference in variability? And variability is measured with the variance. And so that is fascinating. And that's done with an F statistic down here. All right. Then there's sample sizes. And now we're in regression. And in regression, there are hypothesis tests as well, eventually. Blah, blah. Here we go. Knew there'd be more. So, and these are t-tests for beta 0 and beta 1. Prediction intervals, residuals, multiple regression. Just looking for p-values. I did a course like this once upon a time, but my memories are faint.
more better than this?
I feel like it was. Could be rose-coloured glasses. I do remember not really liking one of my second year stats lecturers, because I did 4 stats courses in second year. There were 4 to do, that was all of them. Yes. I remember really loving the other one, so it all evened out in the end, I guess. Okay, so we have some hypothesis tests for contrasts. Which don't produce, oh, it's a t. See, this says t ratio here, so it's a t statistic as well when you do that. So, okay. And hypothesis test for multiple regression parameters, also t's. For beta whatevers. No wonder Gossett won that award for the t-test. Because it's everywhere. Sorry? Okay. Now, I'm almost certain that there would be a hypothesis test for comparing 2 regressions to each other. Like that's an F. No? No, okay. Because in this selection thing, do you use the p-values that go with each parameter? Is that how you do it, with the forward and backward thing? Okay. Yeah. Oh no. Yeah, and that p-value comes from an F statistic, interestingly. What? Here we go. Hypotheses concerning various parameters being equal to 0 simultaneously. This one. That's used with an F statistic. To test the hypothesis that all these betas are equal to 0 simultaneously, then you can use an F statistic for that. But to do a hypothesis for a specific combination of them being, just one calculation being equal to 0, you do a T, but for several of them being 0 simultaneously, that's an F. Okay, F test. What's that? Good times.
We just get the table of distributions.
Oh, so that table back there?
Yeah, that's what we get.
Mm-hmm. Okay.
It'll be like hence show that.
Yep. Okay, that's good. Whether we have to remember all of this or not, it's still useful to have seen it all at the same time, I'm hoping. Because if you know where the thing you're trying to do fits in the scheme, then it's easier to forget everything else temporarily, so you're not overwhelmed. Okay, so these model selection things with the stepwise, like the forwards and backwards and stepwise, are all based on F statistics. So if you look at this here, look at this table, we've got the variable OQ. No, is that the constant? No. The variable OQ, and it's an F statistic here, and the p-value is based on an F. Normally for one variable you'd expect there to be a T statistic there. That F was created by doing this calculation back here. Where did it go? Here. but only for one beta being 0. Because technically you can do a f or a t to talk about one variable, one parameter being 0. Because they do prove elsewhere in the course that t squared is f, basically. All right. Well, I think all the rest of them will be an f's. All right. So for traditional ANOVA, these are all the BICs and AICs things. Yeah. I'm sorry, I don't know much about that. Mm-hmm. R squared? Oh, yeah. So you look at the R studio and it gives you the AICs and the whatever, and you pick the lowest one. Okay. Yeah. Oh, good. Thanks, Ikiki. Is that his name? The AIC is is it Ikiki? Well, could you say the person's name again? Ike. Oh, Aikika. I give up. If they told me how to pronounce it directly, then I would remember it. So then the last thing that happened in first year was ANOVA. And ANOVA generally produces an F, right?
Yes.
And the reason it produces an F is you're asking whether all of the variables are 0. Like all of the parameters are 0 simultaneously. Or they're all equal to each other, so the difference of any two of them is 0. And so you are technically asking yourself whether all of these things simultaneously are 0 at the same time, which is what you're supposed to do in regression to make an F. Multiple parameters all being 0 is you use an F for, so that's why. Okay. So there we go. I'm going to stop there for the moment and make sure that this is our list of everything, I'm sure there are probably some tests involving maximum likelihood, but I choose not. This is my list, which doesn't quite fit. There we go. And you'll see that basically one of them was a chi-squared distribution. Most of them are T's, and some of them are F's. And you go, well, why do I need to know about the chi-squared distribution just for that one? And that's because, technically, a T is a combination of a normal and a chi-squared. So, yeah. Okay. The reason why these are these 4 distributions is because these are distributions that we know, and that we have, if not formulas, at least good approximations for their probabilities. We have formulas at least for the curve, even if we don't necessarily have formulas for the areas, because they're impossible. So these are distributions that are known, and so it's not like you couldn't have done it a different way. Like in another universe, we might possibly have done all of our statistics based on some other distributions, but this is the ones we have that we know. And it's not the worst distribution to have everything that is normal adjacent. Like the chi-squared and the T and the F are all kind of built from the normal distribution, ultimately. And the normal distribution is called so because it's not unusual to see it. And plus the central limit theorem. So, yeah. So I should probably put my money where my mouth is and say about how these distributions are related to each other, so that you can figure out how you get from one to another, because most of the proofs are based on that idea. Is that okay? Talk about distributions? I'm just going to write test mentioned. Now I'm not going to go into more detail on these at this time, but I may. But the point is that it's really important to know what the test statistic is for any given test. And I've written down what letter goes with them so that you can tell. Even if it's not generally called an F test, you know that it uses an F. I think that's useful. Okay. But if you ask R to do any of these in an inbuilt thing, it will automatically produce a value of the test statistic and a p-value. And usually a confidence interval as well. Page 0. Okay. So now we're going to go back and find the distributions, but I'm not going to go through all of them because I know that there's that list at the beginning and then there is Z, F, T and chi-squared. How many is the times? 94 uses of the word distribution. Sorry? A lot less than test, but that was 300. I love the statistics on Statistical Modelling Inference notes. We are looking for a table, so I know what I'm looking for now. Yep, there it is.
That's all we get for the exam.
Cool, and it doesn't mention 3 of the most common distributions, which are T, chi-squared and F. It does have the normal distribution. Okay, so there is a table. It does not have the equations for the curves or moment generating function, which some of the proofs are based on. Is that right? At least one of them is based on the moment generating function. That's a chi-squared, right? I'm pretty sure that's based on an MGF. So it would be nice to have such things. If you need to use a moment generating function, I'm sure they'll give it to you because statisticians themselves don't remember those things. Oh, how exciting. Can I look at the exam one? Ooh. Oh, look at them being nice to us. They have some more. So the exam version of this one, and if you don't mind. Sorry, this is in the course notes somewhere?
It's under like the heading of past exams.
Ah. It's not in this one, but it's in my uni somewhere.
Yeah, my uni.
Which I don't have access to, so. This is the one for the exam. And it does list the PDF. And it also lists, as well as the normal, the T and the chi-squared. It says NA. It does have a PDF. It does have a PDF. It's just that they didn't feel like writing it down. And nobody cares. Yeah, they haven't put the F on there, interestingly, which I think is interesting, because that's certainly one of the distributions we know. But I guess the expected value and the variance is probably not useful. It does involve the degrees of freedom. So interestingly, something worth noting about distributions, I wish I had a printed version of this, but that's okay. Something worth noting about distributions is that each one of them has parameters to tell you what the PDF is, or its expected value and variance. And so you'll see that the binomial has an n and a p, the geometric just has a p, Poisson has a lambda, uniform has a beginning and an end, exponential has a lambda, gamma has a lambda and an a, normal has a mean and a variance, beta has an alpha and a beta, T has a degrees of freedom, chi-squared has a degrees of freedom. So all of you, and F has 2 degrees of freedom. And so all of your famous distributions have 1 or 2, but usually 1 parameter to tell you what it is. And in many of these, the parameter is the mean. Like in the Poisson, it's the mean. In the exponential, it's 1 over that. Yeah. And so, in the chi-squared, the degrees of freedom is also the mean, which is fun. Yeah, and part of the reason to tell you the beta is I believe that the chi-squared is a beta. No, it's not. That's wrong. It's a gamma. Yeah, okay. Okay, so, thank you. I may ask you to tell me things eventually, but... and Z is the standard normal where the mean is 0 and standard deviation. The table in the exam info is more comprehensive, let's say that. Is that right? And just so that you know, go to look at that one, don't look at the one in the notes. Okay. So they mention a whole lot of them. Really nice one is the binomial, which is the probability of x is n choose x, p to the x, 1 minus p to the n minus x, like that. And the mean is np, and the variance is np 1 minus p, I'm pretty sure. Yeah. I can remember things sometimes, and the normal has its own PDF, which is complicated. So these don't have standard letters, the binomial. Normally people just call them x. And then the Poisson as well is a good one. These are discrete. Is that right? Means lambda, variance also lambda. Yeah, I believe in R they call it mu and not lambda. So yeah, they're discrete, and they mention them because they have nice formulas for their PMFs, and they have some nice summation properties. Back in probability and statistics, there were some proofs involving these things with some sums and things, and I'm sure they don't really use them much in this one. No, yeah. So that's great. And so these are like not much, I'm pretty sure. Other than the fact that it's useful to know that the binomial distribution looks like a normal distribution when NP is and N1 minus P are both more than 10. It's one of the inspirations for the normal distribution is the binomial distribution. So that was a distraction, I'm sorry. There's the normal distribution. You all know what a normal distribution looks like. The standard normal distribution is traditionally N1, that's 0, 1. And any normal distribution can be turned into the standard normal distribution if you want. It is, and so it does have a PDF, which has got, you know, a square root and an e to the power of and stuff in it. And the PDF has a name. It's traditionally called little phi of x. And the CDF, which is the probability that z is less than or equal to x, is big phi of x, capital phi. Yeah. And then confusingly at some point in the notes they started using phi for something else instead of this. So fun times for a transformation instead of this. So yeah, but that if you ever see them writing capital phi, then without qualifying it, then it means the standard normal CDF. And importantly, the derivative of this is this, because that's how CDFs and PDFs work. Okay. Cool. Sweet. So the standard normal is kind of so special because you can convert any normal distribution into a standard normal distribution by subtracting its mean and dividing by its standard deviation. So if you have like x is normal with mean and sigma squared, then x minus mu over sigma is normal 0, 1. And in fact, that move will always work. Like even if I just did something random like x minus a over b, that would be mu minus a over b and sigma over b squared. So if you add or subtract a number, it does that to the mean. If you divide or multiply by a number, it does that to both the mean and the standard deviation. That's the general rule. The reason I put that in, so it's like subtract, that affects the mean and the standard deviation, but if you multiply or divide a number, that affects only the standard deviation. That affects, but damn it, the other way around. Add or subtract affects the mean but not the standard deviation, and the multiply and divide affects both of them. Okay, sorry, wrong way around. That's really important because in at least one problem involving power, you had to know that. So, yeah. Okay, and this is the vibe that everything for making t distributions is based on. So if you have a normal distribution and you subtract its actual mean and you divide by its actual standard deviation, you'll get a standard normal distribution, and therefore you would traditionally call it z. Pardon me. But if you divide by it, if you subtract the actual mean and divide by the sample standard deviation, you'll get a t. That's the idea. Yeah. Okay. Cool, cool, cool. So here's the thing. If you have several independent standard normal distributions and you add them together, what you get is a chi-squared. So if you have like z1 squared like that, so these are independent standard normals, then what you get is a chi-squared distribution with k degrees of freedom. Beautiful, classic. Sweet. And when you get two chi-squareds and you divide them, you get an f. I think you have to adjust them by the degrees of freedom. I'm pretty sure it's chi-squared k over k, and chi-squared like m over m is f km. Is that right? Or is it times?
It's definitely division. It might be k minus 1, we don't quite know.
No, I reckon it's k. Yeah. So these are great, but I warn you, they are slightly different to what you actually end up using in the course because reasons. So when you start doing things like the variance of like a sample variance. Okay, so we're into sampling distributions now. These are just distributions. And so just going to step back a bit. So any process that requires you to square normal distributions and add them up should produce a chi-squared distribution. And the variance has that. When you do a variance, so the sample variance is 1 over n minus 1, the sum of, xi minus x bar squared, something like that. Is that right? Sorry? Yep. And that is n squares added together. And so you'd think, except without this bit, right? And I'm making them capitals because we're imagining now that our entire sample is random and every value in it is a random variable of its own. And so what we're imagining here is that x1 up to xn, That's your sample of random variables, technically. And then when you combine them to create x bar, also random variable. Because anything that you calculate from random variables is also a random variable, which means that this is also a random variable, and it has a distribution. And it looks like we've got n, and xi is a normal distribution. So if xi is normal, mu sigma squared, then x bar is also going to be normal, and it will be this. So this is a classic rule. It's not technically the central limit theorem. It's just part of the central limit theorem. So, and this is true for any distribution at all. Whether it's a normal distribution or not, if xi has mean mu and standard deviation sigma, then x bar will have mean mu and standard deviation sigma on root n. That's always true. Yes?
So are we assuming that all our xi's have the same mean and sigma?
Yes.
Okay.
So yes, you normally do them as II. Is that the thing they call it? IID? Independent and so this is a random. Independent and identically distributed. Yes. And that's a big assumption, but it seems reasonable. If you do the exact same process to produce your x's every time, they should all have the same distribution. But yeah, this works even if it's not normal and you just have the mean and a standard deviation, it will still work the same way. The central limit theorem says that even if the original one's not normal, if n is big enough, this is approximately normal. Yeah. Where big enough is talk to different people, you get different answers. So, if your original one is close to normal, it doesn't need much, but most lecturers say 30, which is for, yeah. Yeah. No one will believe you if it's under 10. So, 30 is great because in the Vicar of Dibley Christmas lunch incident, she says, how many advent calendars is the correct amount for a greedy person? And Alice says, I don't know, I would say 30. And so every time the answer for something is 30 in our house, we laugh because of that. So this gives me a small amount of joy that 30 is the number. And I'm absolutely certain that Dawn French did not write that based on the central limit theorem, but I'm going to believe that anyway. Okay, moving on. Okay, so that's great. So what? And when you subtract two normal distributions, you get another normal distribution, right? And so, you know, xi minus x bar will be a normal distribution with mean 0 and standard deviation the sum of these two. When you subtract two normal distributions, you have to add their variances. So that's great. So this looks like it's n standard normals, or n normals anyway, which makes me feel like I should have a chi-squared-ish of... stop telling me these things. A chi-squared-ish of n degrees of freedom, but the problem is that this only works if they're independent, and these things are not independent because they all have x bar in them. And if you do some little algebra and expand it all out and do some magic stuff, you discover that you can rewrite it as n minus 1 standard normals, and it's magic. So, but they're not independent. And magic algebra, it's actually n minus 1 normals. Yeah, fun times. I remember going, oh, that's pretty cool when I learned it. Maybe not the actual algebra, but the fact that it does that way. So, yeah. So what it turns out is that if you get the standard thing and you multiply by n minus 1 and you divide by the real variance, you get a chi-square distribution with n minus 1 degrees of freedom. Yeah. And that's why the n minus 1 actually, because it is a chi-squared, because there's only n minus 1 independent normals. And you also find out that there's another magic thing that happens, is that even though x bar and s squared are calculated from the same data, they are officially independent in a probability sense. And so you actually end up with n minus 1 s squared on sigma squared and x bar, or even just s squared and x bar are independent. And that's not independent in the English sense of not having anything to do with each other, because obviously they do, but they're independent in the statistics sense, meaning that the probabilities of one don't affect the probabilities of the other. And mainly, I mean, if you think about it, when you take a random sample, you get all sorts of different means and you get all sorts of different standard deviations. And any mean technically can go with any standard deviation, and so it all works out fine. So the last thing is that if you get a normal distribution and I'm pretty sure, you have to correct me if I'm wrong, that if you get, did I write it back here? I didn't do the t. I should have put it back here. I'm just going to squeeze it in here. A t with n degrees of freedom is, I believe, a z divided by a chi-squared, possibly with some extra n's floating around. Oh yeah, makes sense. Something like that? Yeah. This is inverted commas, you don't write it that way, but like if you have a z and you divide it by the square root of a chi-squared on n, then you get a t. And that is exactly how you make a t distribution. You subtract the mean, you divide by the standard deviation, and then dividing by that standard deviation will divide the bottom by the standard deviation as well, and so it all works out to be a t distribution. And so what that means is that when you do the original variable minus the real mean divided by the s on root n, then on the bottom you've got the square root of a chi-squared divided by, anyway, it all works out. Like that. Something like that. But I've forgotten the details, but all I know is that this is a t distribution. But there are lots of other situations where you set up things in a similar way and you end up with a t distribution anyway. So every time you have, like in my head, what I'm imagining is if I have like some sort of x bar, sorry, not x, some sort of x bar-y thing divided by some sort of thing with s's under, s squareds under it, with n's as well, then it'll come out to be a t-ish thing. Yeah. And so when you see those formulas all the way through those notes with something with means on the top and something with square roots on the bottom, then you know that's a t. And it was designed specially to come out to a t. So the only reason that calculation was done is so that it did come out to a t, because we set it up specially to be a distribution that we knew. Yeah. So when you go back and look at this list somewhere, which I don't have the formulas for, they'll all be there. Actually, just let me do a proper example, but like we'll just do another example. So when you do the t-test for two means, with unknown, unequal standard deviations, that one. So we've got two means, unknown but unequal standard deviations. So that will mean that your t statistic will be That. And this is of this flavour. Yeah. Oh, S's. What's that? Yeah, show that this is a t distribution. Yeah. So you have to show it's a t distribution. You'd have to look it up. In fact, I might just look it up to be absolutely certain that you've got it. So you have to be sure that I'm just going to look it up just a second. I have to specially share it so that it turns up on the recording. So I know it's double handling. What's that? So that's what I said there with the chi-squared. Oh, look, and they told you the moment generating function. Well, apparently we showed it in workshop 1. I reckon if they ask you to use this, they'll chuck it in a question. Here we go. T. Yep, you were right. It is z on x on chi-squared over p, and then the square root of it. And then the f distribution is coming later, I guess. My instinct was good. You divide each of them by their degrees of freedom and then divide them. Yeah, okay. All right, cool. So if you were going to prove that this was... If you were going to prove that this was in fact a t distribution, you would have to... Let's give it a go. I'm just going to give it a go. Okay, so I'm just going to put in the details. We've got x1 up to x n, or x11 up to x1 n1, and x21 up to x2 n2. These will be normally distributed with mean mu1 and standard deviation sigma 1. And this will be normally distributed with mean mu2 and standard deviation sigma 2. Okay. And then I know that x1 bar will be the sum of x 1 I equals 1 to n 1 over n1, like that. And similarly for x2. And then S, right, so bear with me. So this, and we do know that x1 bar is normal with mean mu1 and variance sigma 1 on n1, sigma 1 squared on n1, and x2 bar will be normal with mean mu2 variance sigma squared 2 on n2. And then x1 minus x2 bar will be normal, because we know they're independent, like everything's independent. We're going to add that there. We know that because x1 is made from variables that x2 is not made from, then they must be independent. And so because they're independent, when you subtract them, the means will subtract. Oh crap, can I just do this? Like that. So in the normal t-test, you assume that this is 0. Yeah, so I'm just going to chuck them in as is now. And then when you subtract two random variables, you have to add their variances. Okay, cool. So I can see the shape of what I've got here. I've got the variable here minus its mean divided by its standard deviation. If we use sigmas in this spot, that would come out to be a z, because they have a normal distribution minus its mean divided by its standard deviation. So that would be a z if they were s's. So my instinct is yes, it should be a t if you use s. So if they were sigmas, it would be a z, but they're s's, so it's a t. But somehow we have to show something. But I do have on the top something with the right, approximately the right thing. So if I go x1 bar minus x2 bar minus mu1 minus mu2, that will be normally distributed with mean 0. To make a t-distribution, technically I would have to divide by the standard deviation as well to make it into a standard normal. So I guess it's not in the formula, but maybe I'll divide both the top and the bottom by this. Let's get a proper eraser. So yeah, in my original formula I don't have this on the top line, but I'll divide both the top and the bottom by this and see what happens. Okay? And then the bottom I need to show is a chi-squared distribution divided by its degrees of freedom under the square root. Okay? Okay. S1 squared. I do know this, that n1 minus 1 times S1 squared is a chi-squared divided by sigma 1 squared is a chi-squared distribution with n1 minus 1 degrees of freedom. This I know to be true. Okay? And same for n2. These I know to be true. And if you add two chi-squared, independent chi-squared distributions, you get another chi-squared distribution with adding the degrees of freedom. That is a fact about chi-squared distributions that we should have said somewhere when we mentioned them. But I know that works because every chi-squared distribution is a sum of independent standard normals. And if you've got two of them, this one will be the sum and the other one will be the sum. And so when you add them together, you just get a longer sum. So just as an aside, if chi-squared n1 minus 1, just aside, if x is a chi-squared with k degrees of freedom and y is a chi-squared with m degrees of freedom, then x plus y, and they're independent, then x plus y is a chi-squared with k plus m degrees of freedom. And it's kind of going that like, well, x is like z1 squared up to zk squared, and y is another set of z's, k plus 1 squared up to zk plus m squared. And so when you add them together, you just get that many z squareds. So that's my reasoning behind it, but you can probably do it from moment generating functions if you felt like it. This is a slightly dodgy argument because just because adding z squares together makes a chi-squared doesn't mean that every chi-squared is makeable from adding z squareds together. But no, that does mean that. No, it does mean that. That's good. I just had to say it out loud to be sure. Sometimes until you say it out loud, you're not sure. And so what that means is that I do know for sure that n1 minus 1 s1 squared over sigma 1 squared plus n2 minus 1 s2 squared over sigma 2 squared is a chi-squared distribution with n1 plus n2 minus 2 degrees of freedom. And that is the degrees of freedom for this test, actually, I believe. Yes, okay, so I think I'm on the right track, doing well. And then somehow I have to wangle this into what I want. Ugh. But I have to divide these by don't actually know what to do here.
It's some sort of multiplied by 1 times the top of 1 less than the square.
Thing.
That trick that I can't remember in my head.
Cool. Yeah, because I'm trying to think of combining this with the thing under here, but pluses do not interact particularly well with fractions. This is correct though, right? Bleh. Have I done that wrong in how to get a chi-squared out of an S? Let's check. So you don't want to be doing this sort of thing in the middle of an exam. Oh no, here, yep, n minus 1 s squared on sigma squared is what the chi-squared is. I'm just going to go and look up if this proof is somewhere. Do you think it is?
I feel like it was in a seminar.
Not in the notes. So 2 independent samples. We've got this one here. Oh, it isn't. It says here it doesn't have a t-distribution. So that's why it says, strictly speaking, it's not even a pivotal quantity. In practice, the quantity is often treated as an approximate quantity for the purpose of making confidence intervals and testing hypotheses. It's approximated by the TK distribution for a suitably chosen K. For what the degrees of freedom is. Okay, I chose a bad one. All right, so I'm just going to write this down. Apparently, nope, just a second. I need to switch my screen. This is not a t-distribution. It's just almost a t-distribution. Wow. So if you drew its PDF to the naked eye, you wouldn't be able to tell. Wow. Wow. Okay. So if they wanted you to show that something was a t-distribution, it wouldn't be this one. Maybe the one with the equal standard deviations would have worked? Yeah. Okay. I'm just going to check that. So if they were equal standard deviations, we go back here. So I was up to this point here, but they've got equal sigmas this time. And so, but they use the pooled standard deviation. Okay. But we can't pool it because they're not the same standard deviation in this one. Okay, I'm just going to write that down just to make sure it doesn't get lost in so if you have t is x1 bar minus x2 bar minus mu1 minus mu2. Damn it. If you do have this on the SP root 1 on n1 plus 1 on n2, that thing, where SP is n1 minus 1 s1 squared plus n2 minus 1 s2 squared on n1 plus n1 minus 1 plus n2 minus 1. 2. Yep, no, that's right. I know this n1 plus n2 minus 2, but it's easier for me to remember if I just put the n1 minus 1 and the n2 minus 1. That pooled then this one will work out to a t-distribution. with that many degrees of freedom. And the reason that will work is that you'll do the same working and you'll get back to here, but they'll both be sigmas this time. And because you're capable of dividing them both by the same sigma, you'll be able to make it turn out to be the right distribution that you want. Yes. Yes. Okay. Right. That's okay. And I just, wait. Ugh. So just to be sure, I just want to be absolutely sure, the first part of the working will be the same, this x bar bit will be the same. Yeah. So just the same working as before will be that x1 bar minus x2 bar minus mu1 minus mu2 over the square root of sigma squared on n1 plus sigma squared on n2 will be a z, like a normal, standard normal. And you'll be able to factorise out the sigma squared. Yep, that's great. And then, since this thing isn't in the other one, we're going to have to divide the top and the bottom by that, but we're going to do the same working, and we'll do more working n1 minus 1 s1 squared over sigma squared plus n2 minus 1 s2 squared over sigma squared is a chi-squared with n1 minus 1 plus n2 minus 1. And so, how are we going to get our t distribution out of this? We can pull out the sigma squareds. Yep. Like that. Okay. And so if you divide top and bottom by of the t thing here, oh, I see. Just checking. So my SP is this thing here. Oh, okay. So the 1 on N1 plus the 1 on N2 is pulled up to the top line. Okay, just a second. So T equals x1 bar minus x2 bar minus mu1 minus mu2 over SP root 1 on N1 plus 1 on N2, like that. And you can then rewrite that as x1 bar minus x2 bar minus mu1 minus mu2 all on root 1 on n1 plus 1 on n2 divided by SP. And then I can also divide the top and bottom by sigma. Yep. And that gets me my standard normal on the top line. And then on the bottom line, SP divided by sigma is exactly, wait. Where'd it go? Oh, it's just actually on the same page. SP divided by sigma is, got the n minus 1 right, I'm missing something. So SP, oh yep, that's fine. Yep, and so this here is 1 on sigma squared SP times n1 minus 1 plus n2 times 1. This is SP like that, because SP has got that on the bottom. And so if I multiply it over here, we get this thing. Aye. And so SP divided by sigma, look at that. I think I'm right. Wait, so this thing is a chi-squared, right? Too early in the morning for this. We're nearly there. I thought I was there. No, that's okay, because you have to divide by the degrees of freedom as to do the t. Yeah. And so we're going to add into this the same top line that we had before, and we have SP times n1 minus 1 plus n2 minus 1 over sigma divided by n1 minus 1 plus n2 minus 1, like that. And then this bit is a chi-squared. Well, we'll pop that in after we've done the squaring. So we'll whack a square root in here and pop these in, and then we'll put the n1 minus 1 plus n2 minus 1, n1 minus 1 plus n2 minus 1, and then all of that bit there, that's a chi-squared. Yes, yes. And so what we have is that the numerator is a standard normal, and the denominator is the square root of a chi-squared distribution divided by its degrees of freedom. Yep. So I should give this a name. I shall call this W. Denominator is W on the degrees of freedom of W, where W is a chi-squared with n1 minus 1 plus n2 minus 1, and therefore T is a T distribution with n1 minus 1 plus n2 minus 1 degrees of freedom. Okay, I in fact had all the pieces, I just couldn't see them. So the reason why so this SP, which is actually a natural thing to do, but the reason it's divided by this number in particular is because that is the degrees of freedom of the combined chi-squared distribution. Because if you wanted to get a combined standard deviation, you need to have everything minus its mean squared, which is what this thing here is, and add it up, and this is everything minus its mean squared of the other one. And so when you do that together, that is everything minus its own mean squared added up, so it is a standard deviation. It's just that we haven't subtracted the grand mean of the whole group, we've subtracted the two individual means. And so because of that, the degrees of freedom isn't just the total minus 1, it's a little bit less. Yeah. Okay, so they've done this, and then it turns out that when I made my chi-squareds the way you normally do from a standard deviation, part of that was in that pooled standard deviation formula. So we had to twice in this working rearrange fractions and divide top and bottom by stuff. So the first move, we divide the top and the bottom by sigma, and then we put this under a square root, and inside that little fraction we divided the top and bottom by the degrees of freedom. Yeah. Wow. Okay. Gosh. Clever dudes in our 20th century statistics, honestly. Okay. Right. So just to be absolutely clear in my own mind, the other thing that could happen is that you could try to do a true samples with standard deviations. S1 is like 5.8 and S2 is like 12.3 or something. Is this evidence that the standard deviations are different? So that means that we need to construct from this information that we have, oh no, we need the sample sizes. N1 is like 20 and N2 is like, I don't know, 30. Let's do that. Right, so we're going to assume that they're normally distributed, whatever. And so, is that evidence that the standard deviations are different? We have to create a test statistic out of the information that we have. And we do know that S1 squared times N1 minus 1 over whatever the real standard deviation is a chi-squared distribution with N1 minus 1 degrees of freedom. And we know that N2 minus 1 times S2 squared over S sigma 2 squared is a chi-squared distribution with N2 minus 1 degrees of freedom, where sigma 1 is the true standard deviation in situation number 1, and sigma 2 similarly. Officially, if you're showing working and you introduce a letter that isn't already there, then you have to say what it means. And somehow we have to compare these two standard deviations using a distribution we know. We do know that the standard deviations already are almost a chi-square distribution if you fiddle with it a little bit. We have to combine them somehow. So the two ways to compare numbers are to subtract them or to divide them. And earlier we said that when you divide two chi-squareds, you get an F. Yep. So we do know this. So I'm going to do this. My null hypothesis is that sigma 1 is equal to sigma 2. I know that the lecturer would probably put sigma squareds there, that's fine too. And if I assume they are equal, under the null hypothesis, I'm going to let sigma be sigma 1, which is the same as sigma 2. Because then when I do my working, N1 minus 1 S1 squared over sigma squared will be a chi-squared with N1 minus 1 degrees of freedom, and N2 minus 1 S squared over N sigma squared will be a chi-squared distribution with N2 minus 1 degrees of freedom. And if I divide those two chi-squareds divided by their degrees of freedom, I will get an F distribution. I'm just going to call this W1 and W2 so that they have a name. W1 divided by W2, W1 divided by N1 minus 1, and W2 divided by N1 minus 1 will be an F distribution with N1 minus 1 and N2 minus 1 degrees of freedom. So if you get a chi-squared divided by its degrees of freedom and another chi-squared divided by its degrees of freedom, and they're independent, you'll make an F with the two degrees of freedom for the top and the bottom. And if I do that, so I shall call this F. So F is W1 divided by N1 minus 1, W2 divided by N2 minus 1, which is, so this divided by N1 minus 1 is S1 squared divided by sigma squared. And this one divided by N2 minus 1 is S2 squared divided by sigma squared. And the sigma squares cancel and I get S1 squared over S2 squared. Yay! So I've just proven, not that it was necessary to prove this probably, I don't know, but I've just proven that if you just divide the two variances, it'll be an F distribution. Under the null hypothesis anyway. If it's not the null hypothesis, that will not be a F distribution. And so I will get my F statistic is 20, no. So I don't even need the sample sizes. That's amazing. I thought that I would be needed to tell this information, but apparently, I do. Oh, yes, I do. Nope, I don't.
But don't you need it for the degrees of freedom for that?
I need it for the degrees of freedom. Excellent, but I don't need to do this calculation. So for the purposes of finding F, it's the value of F. I don't need the sample sizes, but I do need it for the degrees of freedom. Thank you. I told you to interrupt me, and you did. So you're doing well. And so this will be 5.8 squared over 12.3 squared, which my calculator says is 0.22. Interesting. I probably should have done the big one divided by the small one. But anyway. So, when I draw an F distribution, which is how an F distribution looks, the peak is normally at approximately 1. I think it's at like what you get, I don't know, doesn't matter. It's on this side. So, being worse than that would be here. The thing is, and so this is an F with 19 on the top and 29 on the bottom. That's what this is. So that's part of my p-value. My other p-value will come from the F that was calculated the opposite way round. So we could go like F dash is 12.3 squared over 5.8 squared, which is 1 over this. Which is 4.4, damn it. $4.497. And then there's a different F distribution, 4.497, and then this would be worse. But this is an F with 29 on the top and 19 on the bottom. Those two probabilities added together, that's my p-value. Is that okay? Yep.
So whether you're looking at like below your F statistic or above your F statistic, does that depend on the order of the degrees of freedom, or depending on whether you got the bigger number on the top and the smaller number on the bottom?
It depends on whether the bigger number's on the top or the smaller number's on the bottom.
Okay.
Because my reasoning is this: I would be, if the standard deviations were equal, I would be more surprised if this number was even smaller. But this number getting bigger would just make it closer to this number being 1.
Okay.
Like the number 1 is when sigma 1 is equal to sigma 2.
Yeah.
And the number 1 on this one is when sigma 1 is equal to sigma 2. And so the further away from the null hypothesis is that way. So this is where, this is kind of where the null hypothesis lives. Yeah, that's what I'm thinking. Yeah. So I was actually thinking, well, 1 would be what I would get if they were equal, and I want to go further away from that. Yeah. Okay. And whatever those are, which you would need a computer, or perhaps the person doing your exam would give you some R code and say, here's some thoughts. And if I were asking this question in an exam, I would give you 4 pieces of R code. I would give you PF 0.22 with 19 and 29, PF 0.22 with 29 and 19, and the same number with this with both of the others. So you had to choose out of those 4 which 2 you wanted. Yeah. Or possibly an F table, but is much more likely for them to give you a selection of R codes. Or to not ask you for the answer, but just to write it as a probability thing. And so the p-value is the probability that f is less than 0.222 plus the probability that f dashed is greater than the 4.497. Yep. Because it was a two-sided one. If it was one-sided, then you would just do one of them. Which I actually think is probably going to be quite small. I don't feel like waiting for R to fire up to ask it the question. Yeah. Nice. I'm really happy about that, actually. That makes me happy. I like that I was able to reconstruct what the test statistics should be, which is the natural thing you would do. You just divide the two standard deviations. But isn't it interesting that the one for standard deviations is much more natural than the one for the t? Because for the t, you've got the difference between the means, yes, but then you've got this crap on the bottom. But this is just clean. I quite kind of like it. I will try to remember this feeling next year. Yeah. Okay. Right. Well, I've got like 15 minutes to 30 minutes. Can always start the real analysis one a little later. I do want to say that I've basically talked about this stuff. I've talked about p-values more or less and sampling distributions. But those proofs, notice that proof didn't use moment generating functions. It just used facts about chi-squared distributions. And I think that to me is probably the more likely thing that they're going to be interested in your exam. I can't be sure, but my instincts are that they're much less interested in the prob and stats proofs. They're more interested in the proofs that were unique to this course. So proving that something is a chi-squared with its moment generating function is a very prob and statsy sort of proof. But proving that something is a t based on showing that this is a z and this is a chi-squared is much more this course, because it's the only proof that's only in this course and not in the other one. So that's my instinct. So yeah, that's my usual when I was a student. It's like when I'm helping people with Maths 1B as well. It's like, well, this is a very Maths 1A sort of proof, so I wouldn't expect them to put it in Maths 1B because you saw it in Maths 1A, and they need to test the new stuff. Yeah. Okay. Right. So the other things are confidence intervals, which are done with pivotal quantities, as far as I recall, and regression, which is regression. So ultimately, one of the things that's always been confusing to me about regression is the model and then writing it with the matrices. So I'm just going to say a bit about regression. So the general idea of regression is to have some sort of numerical outcome being affected, at least predicted, by various other things. That's how I think about regression. So that's a scale to measure the number on. And that outcome is traditionally called y, and these are traditionally called x's. And it's totally possible for these things to be numbers, but it's also possible for these to be categories. So when you do this, that's simple linear regression. You're trying to predict an outcome from a numerical outcome from a numerical input. But this is ANOVA, traditional ANOVA. You're trying to predict a numerical outcome by which category you are in. And, you know, this is just multiple regression with some dummy variables. This is ANCOVA. You're trying to predict a numerical outcome from the group you're in and some other variable, which is called the covariate. Is this helpful? Yeah. So that's multiple regression. This is simple linear regression. This is ANOVA, and this is ANCOVA. Just in case you're wondering how my mind works. And you technically can mix any of those things together into a great big multiple regression. But since you're at the end of the course, I can talk about it this way. And the way you set it up is that each numerical variable will go in with a coefficient, and each categorical variable will go in with a mean for each group. Except one of them won't be there. There's one group that you're going to compare everything else to. And so this will go in, I'm just going to draw a new picture. This will go in with like a beta 1 x1 in the formula. A, B, C, something like that. This will go in with like a each of them will have a mean of their own. So mu A, mu B, mu C. And then this will go in with a mu A plus mu B minus mu A being in XB, and mu C minus mu A for being in XC. Something like that. That's what it will look like in the formula. And in the notes they called these betas, but that's the idea. And this mu A will end up absorbed into the constant term. So technically it's not there, but whatever. So essentially you're going to have a variable. This xb is the variable that is 1 if you're in category B and 0 otherwise. And this one's 1 if you're in category C and 0 otherwise. And then to be in category A, you just need both of those to be 0. So in category B, xb equals 0 and xc equals 1. And in category C, xc equals B equals, damn it, xb is 1 and c is 0, sorry. xb is 0 and xc is 1. And in category A, xb is 0 and xc is also 0. Is that all right? Yeah. So, but what you don't want to do is put an XA and an XB and an XC, because you won't be able to tell everything apart. Your matrix that you make will end up being linearly dependent. And I'm sure that was a proof in one of the assignments or workshops or something. But anyway, you can't do that. Yeah, and that's basically it. I will say that sometimes you have interactions between the variables. And that's very common in ANCOVA. If I actually draw ANCOVA properly, ANCOVA is actually this, but this category will affect the way that that variable affects this. That's actually ANCOVA. The covariance is talking about this relationship, and we're saying that this affects the covariance between those things. Yeah. So the category affects the way that X affects Y. And that's called an interaction. And the way you deal with interactions is just multiply the variables together. And stick an extra variable in for that. Yeah. So for this one, this would go in with just an xb, for example, the same as this one does. There wouldn't be two variables, there'd only be one for the extra you get by switching from A to B. And so in ANCOVA you would end up with your y is, bear with me, there would be a beta naught and there would be a beta 1x, and then there'd be like a, you can call it beta if you want, but there'd be a mu that goes with the x. There'd be a beta 2 to go with xb for being in category B, and then there'd be beta 3 for the interaction, like that. So this is the numeric variable. This is xb equals 0 if in 1 if in category B, and xb equals 0 if not. And this is the interaction. And what this means is you'll only get this if you're in category B. You'll get a little bit of extra. The relationship between x and y will be different depending on the fact that you're in B. So if this is 0, this coefficient here, then it doesn't matter whether you're in category B or category A, you always get the same extra when x goes up. But in this one you get a little bit extra, even more when x goes up. So what happens is that if you're in category B, you get y is beta naught plus beta 1x. Beta 1 plus beta 3 lots of x, because in this one category B that and plus a beta 2. And so with this being 1, that beta 2 is just there. With this being 1, this is what it is when you're in beta 2. When you're in category B. But in category A, xb is 0 and you just get this. Yeah. And if you think that the intercept shouldn't change, damn it, can I just move the beta 2 over here? So what happens is that being in category B changes both the intercept and the slope. But if you don't want to change the slope, then you'll have to do something to fix that. You'll have to make beta 2 like something else. Beta 2 minus beta. I'm not sure how to do that, but that's okay. Okay, yay. So, and then you just run the regression and each thing will have its own coefficient in the table and its own p-value in the table. Yeah. So then, technically all of these have little eyes on them, and then there's like an epsilon at the end. Like, something like that. So the concept is that the universe, in its wisdom, chooses the value of y by this process. Does this little calculation and then adds a bit of randomness up or down. And so this is straight up regression where the purpose is to decide a formula. But in order to decide the formula, you have to ask a whole lot of yes or no questions, which are, should this variable even be here? Which is a yes or no question. And that's the same as saying, should this coefficient be 0 or not? And so to ask if a single coefficient is 0, we wrote that down right at the beginning. A single coefficient being 0 is t-test. They're all t-tests. Because maths says that they're all come out to the same sorts of calculations as long as this variable is normally distributed. It's very important to notice that the only place where the randomness comes from in this story is here. All of these x's are not random. That's part of the theory of this. Because this is designed, remember, all of this was designed for the purposes of agriculture experiments when they first invented it, right? And in an agriculture experiment, you get to choose how much fertilizer you put on and which field you put things on. And so all of these X's are chosen by the researcher. They are not random. But even though in a real experiment, one of the variables might just be rainfall, which you don't get to choose, you're still going to pretend it's not random. Because when you do your predictions, you're going to say, suppose the rainfall was this number, what would the Y work out to be? So even though technically it's random in real life, when you're predicting, you are pretending it's not. So that took me a while to get a handle on. But the X's are not random. Yeah, they are not random variables. Some courses, when they do all the probability calculations with this, will go given the values of X. They'll actually be conditional probabilities. But in this course, I don't think they do that. I could be wrong. Yeah. So anyway. And then, it's fun times. This was all invented, at 1920s-ish. The original recipe version of this. Matrices were only just starting to be a thing that people cared about around that time. Matrices only became a really big thing when computers were invented. So, yeah. But you can imagine that every individual Y is calculated like this, and look very closely, this is a dot product. It has some betas multiplied by some other stuff and then added together. And dot products are what matrix multiplication is. And so the way we imagine this is we imagine the betas as a column vector and everything else as a row vector. And so we're imagining that yi is this row vector of x's times this column vector of betas plus a bit of epsilon on the end. That's how we're imagining it. And if you have a whole lot of these things, like a whole list of yi's, then you can just imagine a whole list of these all multiplied by the betas one after the other, which is how matrix multiplication works. So if you have like y1, y2, y3, blah, 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 then all you have to do is keep the betas and have 1, x1, xb1, x1, xb, 1, x2, xb2, x1, x2, xb2, blah, 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 and have a big matrix here. And then you get epsilon 1 up to epsilon. This is the only way I know how to do this. I always start out with saying, well, what does one row do? And then you've got this, and this matrix is traditionally called capital X. Is that right? And is it called the design matrix? No? Okay. In some courses, they call this the design matrix. Because remember, this is all because of an experiment. It's the experimental design. Yeah. That's why it's called the design matrix. So if you ever want to Google this, Google design matrix for regression. Yeah. And this, yeah, so there you go. And all of your regressions can theoretically be set up this way. Yeah. And so you have this vector of y's is this matrix times this vector of betas plus this vector of epsilons. And this is like a n by 1 column vector. And this is a however many parameters there are by 1. This is also n by 1. And this has to work out to be a matrix that's also n by 1, so it must be n by k. And this isn't going to work. You're never going to be able to figure out. So just step back a bit. Your goal is to try and predict a value of y from the values of the x's. That's the goal. And so you're trying to strip away the randomness. And so you will have this thing where you have y hat, the value of y hat, will be a row of x's times some beta hats. Something like that. Because you will have all of the matching. We're trying to do this calculation for a single y when you try and predict something. Yeah. So the question is, what is the best choice of this beta hat? What is my best choice of what the betas are that makes all of the answers here, x beta hat, as close as possible to the actual values of y? Not that I know what to the actual values of y that I actually have. And what that means is that we want to make these epsilons all as small as possible. And so ultimately we try and make the square of the epsilon hats, the sum of that as close as 0 as possible. And it turns out, thanks Fisher, that it is orthogonal projection, as per algebra 2. It's pretty cool. Let me see if I've got it right. There's like an x transpose and an x, and then and that inverse and something, right? So just bear with me. I'm going to try and remember it, and then we're going to look it up, okay? So, was it what? Ah, okay, cool. I don't have access to that, but that's all right. I'm pretty sure it's x transpose x, x inverse x, y. Transpose? Yes, that makes sense, because the dimensions won't line up otherwise. Because this is an n by 1, x transpose is a k by n, and inside this we've got an k by n times n by k, and so that will be a k by k. Yep. And then the final answer is supposed to be k by 1, and that will work. The sizes are right. Okay, excellent. And here's the thing. What you need in order for this to work is for x transpose x to be an invertible matrix. It is a square matrix, it's k by k, but I need it to be invertible. And for it to be invertible, I need the columns of x to be linearly independent. So for x transpose x to be invertible, we need the columns of x to be independent. Yeah, and that will be enough. And if you do put in a variable for, like, you've got your A, B, C, like I said before, if you put a variable in for A and a variable in for B and a variable in for C, you're going to guarantee that the 3 columns for those variables won't be independent. Because one of them is going to be the difference of the other 2 or something like that. So that's why you can't put them in from the matrix algebra reasons, but also just from philosophically. And from a science reason, one of them is the control group. And so you compare everything to that. And so it is useful to think about the fact that this came about from agricultural science. Yeah. Our plant science building used to be called the Fisher building. They knocked it down because it was in the way, because the heritage laws, which, I mean, it was there for like 40 years, but the heritage laws say that Bar Smith Library has to be visible from Frome Road, and so they had to knock down a building that they built between the Bar Smith Library and Frome Road, and that was the Fisher building. Also, it was full of asbestos, so, you know. Also, Fisher sucked. Like, you know, he did some good stats, but he was a horrible person. Yeah. So I'm not unhappy that we don't have a Fisher building anymore. There are people who are still campaigning to try and get his name off of a scholarship. Because what he used statistics for after he used it for agricultural science was eugenics. Yeah. Yes. He was the editor of the Journal of Eugenics. Yay! Anyway, thank you for the algebra, Fisher, but everything else, no thank you. So, yeah, and it's just super cool that that works. And as long as you can imagine your situation to be writable in this format, then you can use the matrices to do the trick. If you ever study a course which says something along the lines of statistical machine learning in the title, or maths for machine learning or something, you will probably do this proof using matrix algebra, matrix calculus, which is fun. And so, yeah, because you imagine that you're trying to minimize this, and so you differentiate with respect to a vector. Yeah, it's just multivariable calculus, but in short form. So yeah. So yeah, my memory works like I'd have a picture. I don't have a picture. I have this blob in my head, and I know it's got x's, and I know it's got y's, and I know that there's several x's, and there's transposes and inverses, and then I have to write it down and hope that I put them in the right spot. Yeah. What's that?
Did you know that this process can be split into two?
Yes, I did know this.
Oh yeah, I told you yesterday.
Well, no, you didn't. But I was told earlier. So, and Jono has been very excited about how he split these courses up and when he's been writing them. So, because Jono is incapable of being not excited about any of his work. So, hello, Jono Chuk. Yeah. So yeah, and I am actually very happy that he's made a good attempt to split them up in a useful way. And yes, this course has too much in it for one course, so it should be split up if you want it all in somewhere. So yay, future students. Suck it, you guys, I suppose.
Technically, the last cohort is like all the other previous cohorts have been too.
Yeah, I know. I don't know. Yeah. Anyway, so the only other thing is that pivotal quantities and well, there's lots of other things. Let's be honest. The only other thing I really wanted to say is, if I had time, which I have about 20 minutes, is the pivotal quantities thing for confidence intervals and or power. They're the things on my mind, but you can ask other things if you like. All right, I'm going to just mention this confidence intervals and pivotal quantities. According to the notes, a pivotal quantity is a thing that you calculate from the data that doesn't have the parameter of interest in its distribution. So, so you calculate it from the data, like your x1 up to x whatevers, or y1 up to y whatevers, doesn't matter. And its distribution is describable without the parameter. So a pivotal quantity for parameter theta, its distribution is describable without the parameter theta. And so it's a little bit like a basis in the sense that there's no such thing as a pivotal quantity. There are only pivotal quantities for things. And a pivotal quantity for theta might not be a pivotal quantity for something else. That's the important thing. That is an important thing. And why would you care? And you would care because then it's a distribution that you know for sure. It's like Z or T or F or chi-squared. Those distributions don't have the parameter of interest in them. So when you go looking at this chi-squared thing where you divided by the sigma, right? This sort of thing, right? The quantity itself does mention sigma, but its distribution doesn't. And that's an important feature. Your pivotal quantity is allowed to mention the parameter, it's just that its distribution doesn't. So you can calculate it from the data and you can calculate it from theta as well if you want. That's important. So your T statistic is a pivotal quantity for the mean. And it mentions the mean in it. And that's okay, but its distribution doesn't mention the mean. Yeah, that's the difference. So for example, S1 squared on sigma squared n minus 1 is a pivotal quantity for sigma. I think that's right. Because it's distributed according to a chi-square distribution with n minus 1 degrees of freedom, which doesn't mention sigma. No sigma mentioned. Yep. Took me a while to figure out what the hell that was on about. And the reason you would want to do that, such a thing, is so that you can make hypothesis tests and confidence intervals. Because hypothesis tests are much easier to look up if you know the distribution. And if this mentions sigma, which you don't know, you don't actually know the distribution after all. That's the problem. Yeah. So, showing something as a pivotal quantity means finding its distribution. So, because the deciding factor is that the distribution doesn't need the parameter to describe it. So you technically don't need the name of the distribution, you just need something that describes the entire thing. So if you can get it down to this, then that's great, but you could also get it down to a moment generating function, or you could get it down to a PDF. Yes, I know it's coming. It could be a PDF, it could be a CDF, it could be an MGF, it could be a name. Like, any of these things are okay, and as long as the description you have does not include the parameter, it's a pivotal quantity. So there were assignment questions in this course, at least this year or previous year, that said, show this as a pivotal quantity, and what you got, you went, okay, well, I don't really know what distribution it is, but I've got its PDF, and it doesn't have theta in it, so cool, pivotal quantity. That. You okay? Security dude keeps staring at me. Sorry? Must be bored. Like, and if you're bored, statistics is the thing, I suppose. So, if you have a pivotal quantity, you can make an attempt to make a confidence interval from it. So here's the thing, this is the example that's in my head. Confidence interval for sigma squared. Okay? So, a confidence interval for sigma squared would be a pair of numbers like that. I'm going to put a 95% confidence interval so that, here we go, the probability of a random one of these things containing sigma squared is 95%. That's what a confidence interval is. I'm just going to write that in words. Probability of a random LU containing sigma squared is 95%. That is what a confidence interval is. That's what it's supposed to be anyway. And look, we've made a probability statement. There must be a random variable here, and our random variable is in fact two random variables, the number L and the number U. You can't make probability statements about variables that aren't random. I mean, you can, but the probability is either 0 or 1. Okay, so we need the probability that LU contains sigma squared to be 95%. That's what you need. I know that the lecture doesn't normally start there, but this is the only way I can make my brain do it. Okay. And so I'm going to take this statement that LU contains sigma squared and work on that. Doesn't really matter whether it's an or equal to or a less than, it's a continuous variable. Okay, and somehow I need to work on this. So here's the thing. This is an unusual statement to put in a probability because it's got two random variables in it. I would really much prefer to make a statement about one random variable. And that's how the works for me. I want a random variable in the middle and numbers on either side. That's what I want. So I'd prefer number less than or equal to random variable less than or equal to number. That's what I would prefer. Yeah. So I have to create the number that I want. And in particular, I would prefer this random variable to have a distribution that I know that doesn't mention sigma squared. I would prefer that this to be a pivotal quantity for sigma squared. That's what I want. Because then I'll be actually able to calculate or at least imagine the probability that I want. So this is my reasoning to convince myself that pivotal quantity is a thing that you would want a name for. Why would you want a name for this damned thing? And the reason you want a name for it is to describe what you're aiming for in order to create a confidence interval. You only need names for things that need talking about. Okay, so I need to create my pivotal quantity, and my pivotal quantity is n minus 1 s squared on sigma squared. That's my pivotal quantity. So I need to, damn it, I need to create this thing in here. So, sigma squared's on the bottom, I'll divide by it. But when you reciprocate numbers, you have to flip the inequality signs. And technically you're only allowed to do this move if all the numbers are positive or all the numbers are negative, but whatever. sigma squared can't be negative anyway, so that's fine. And so they wouldn't have you put a negative number here because it can't be negative, so that's okay. And then I need to multiply by n minus 1 s squared. And now I have created my pivotal quantity in the middle. I shall call said pivotal quantity x. And just to make my life a little easier, because I don't like inequalities that are written in this direction, I have that n minus 1 s squared on u is less than or equal to this number x, which is less than or equal to n minus 1 s squared on L. So I did two moves here. I called this x, and I moved it around so that it was pointing the right way. And now what I want is the probability that this is true to be 95%. And lo and behold, I have the statement I want, the kind of statement that I'm used to when talking about probability distributions, that has a random variable in the middle. And I know technically S is a random variable, but don't look behind the curtain. That has a random variable in the middle and numbers on the outside. And so I can go, cool, here is my chi-squared distribution, and here is my two numbers. This is n minus 1 s squared on u, and this is n minus 1 s squared on L, and I need this probability to be 95%. That is a picture of this. And this is a chi-squared distribution with n minus 1 degrees of freedom. And so there are in fact many ways to choose what these two are so that the middle is 95%. And traditionally you just make this bit 2.5% and this bit 2.5%. And so we now declare that n minus 1 s squared on u is equal to the position in the chi-squared distribution with 2.5% below it, which unfortunately is written like this: the position with 97.5% above it. So when you write a traditional name of a distribution and then brackets a number, what you mean is that there's that percentage above. It took me ages to figure that one out too. And then n minus 1 s squared on L is now chi squared n minus 1 0.025 because it has it above it. And now you rearrange this and it'll tell you what L and U are. What's that? Yes, because this in R is 1, wait. This in R is Q chi squared 0.025 n minus 1. Is that right? Is that how you do it? Q? Because R is written in such a way that it always accepts the left-hand area. So in R, this is Q chi squared 0.025 n minus 1. And this one is Q chi squared 0.975 n minus 1. Yep.
But you should just be able to tell which is one of them.
That's right. If you've done the wrong one, then yeah, this will be the small one and this will be the big one. Yeah, that's right. As long as you've drawn your diagram with the correct U and L in the right spot, then you can just, if they give you some R code, you'll go, right, I'll take the big one. Thank you. Yeah. I will say that you can actually tell the Q chi squared to give you the left tail. There's a comma left tail equals true or something. But I can never remember what that command is. And if I was in R, I would just do tab and see what it said. Lower dot tail or something like that. And it's traditionally false because CDFs are normally the left-hand side. But this notation gives you the right-hand side because it's designed for the normal distribution where the right-hand side is the same number as the left-hand side, it's just negative. Yeah. Yeah. And so you would rearrange this and you'll get, when you do this move that we just made here backwards, you will get that n minus 1 s squared on u is chi squared n minus 1 0.975. And so you'll times by u and divide by this, and that'll tell you what u is. So n minus 1 s squared on chi squared n minus 1 0.975 is what u is. And also n minus 1 s squared on chi squared n minus 1 0.025 is what L is. Yeah. So people ask me several times in the Maths Learning Centre, like, oh, why is the lower one calculated from the upper? The lower one calculated from the upper one? Is it always true that the lower one's calculated from the upper one? And the answer is no. It's just because the sigma squared's on the bottom in my pivotal quantity. If the sigma squared was on the top in my pivotal quantity, they would be in the same order. Or possibly if there's a minus though, sometimes it works out the opposite way as well. It's just based on what happens with the algebra when you do it. And I know it always seems to me like double handling to come down to here and then have to go back, but that's just how the argument works. Sorry? Yeah. So anyway, I just wanted to talk about that. And now we will really stop and we'll do real analysis instead.
Sorry, can I ask a really dumb question?
You can ask any question.
So after we've done all this, what is our pivotal quantity?
Well, the pivotal quantity, what I did just there was not finding a pivotal quantity.
Okay.
What I did was beginning with a pivotal quantity.
Right.
In this one, I'm finding a confidence interval using a pivotal quantity.
N minus 1 s on
Sigma squared. And so this, I have, at this point in my working, I had achieved my pivotal quantity here. Pivotal quantity achieved. Right. Okay. That'll do. I hope that was useful. Right. Just anyone who's watching this and just for you guys, Maths Learning Centre is open all the way until the 19th of December. Possibly closing on one of those days because there's a end of university party or something. But yeah, from the end of this week it's 10 a.m. to 4 p.m. Monday to Friday. From next week it's 1 p.m. to 4 p.m. Monday to Friday. Someone will be around. I personally will be around most of the time, on and off. But just I'm the coordinator. I have to go to all the merger meetings, so just be aware of that. Yeah, and look, if you all go at the same time, you can support each other and have a little pass session when there's no pass leader. So yeah, I will email you all these notes. And farewell on your exam.